The purpose of this special report is to present a concise picture of the space resources which the Air Force has developed in order to acquire for the United States a new line of sight. The official Soviet announcement of their unilateral cancellation of the nuclear test ban was followed by the detonation of 14 devices within 3 weeks. The details of preparation for their special weapons tests must have extended over an appreciable period of time. Time itself has become a weapon, and the time element is an integral part of this report. It has been just a little more than 7 years since the Air Force initiated its accelerated ballistic missile program, which today is providing the nation's booster springboard into space. The success of the basic hardware of deterrence and space makes good copy. But the real importance lies in the buildup of the solid foundation of the total program, the coordinated human and physical resources that together mean ability to produce. In the interest of national security over the full range of the aerospace environment, that ability to produce has been steadily advancing since 1954, when, for technological guidance and advice, the Air Force called upon its Scientific Advisory Board. And they responded, men like von Neumann, von Karman, Kistiakowsky, Millikan, Draper, Ramo, and Teller, Kaplan, Getting, Stever, and all the others. In the pioneering tradition of General Mitchell, they accepted the challenge. Development industry from the Pacific to the Atlantic was called upon for diversified sources of production and people for new and exacting skills. They responded and they worked. Advanced new concepts have applied and proved out new disciplines of management, with all phases moving forward together at the same time. Development, production, site activation, support equipment, crew training. For easing the heavy weight of time, systems management is a powerful lever. The fulcrum is the critical examination and decisive trial of testing. Parts, components, subsystems, whole systems, and the total weapon. Thousands of tests of subjection to conditions that show the real character of things and people. Neither things nor people are perfect. The planning, the effort, and the calculated risks may be important only to those who overcome the technological obstacles, or to the ones who make the management decisions, or the many others who follow through to ensure that R&D actually works. But what they have accomplished is important to everyone, as all phases of planning and production keep pushing steadily ahead, with emphasis on reliability. Atlas, operational in the hands of SAC, although at first unprotected, has been advanced to a partially hardened configuration, and later missiles will be dispersed in fully hardened silo lifts. Minuteman, our light solid propellant ICBM, has from its concept been designed to fire from the hull with almost instantaneous strike-back capability. The upcoming Titan was our first ICBM with the silo lift configuration, and Titan II's storable liquid propellants make it possible to equal Minuteman's fast reaction and combine it with extreme long range and a strike-back power capable of destroying any hardened target. An advanced Titan will be used to place Dinosaur, a manned glider, into orbit. For such manned spacecraft of the future, the X-15 is currently serving as a transitional step. It is logical that the power of the boosters and the experienced resources of people and the precision production capability developed by the ballistic missile effort should prove to be a long right arm in the big reach toward space. As early as October 1958, Thor-powered Pioneer 1, 71,300 miles from Earth, our first deep probe into the new aerospace environment. By 1960, gratifying successes began to come more frequently. Launched in March, Pioneer 5, en route to a solar orbit, sent back valuable data for a record 22.5 million miles. Launched on April 1st, a Tyros weather satellite recorded and transmitted some 22,000 photographs from altitudes up to 450 miles. In mid-April, Transit, the navigation satellite, was Thor boosted into orbit. Since September of 1959, the Air Force has provided and launched boosters for the space programs of all military services and for NASA. Thor has been the reliable workhorse. But even before Thor was successfully airborne, the Air Force Systems Command was pushing ahead with the Discoverer program to develop a space vehicle capable of carrying out a number of useful passive military missions. The resulting upper stage vehicle, a Gina, can be reoriented. It can be directed and controlled. It can communicate and restart. A key objective of the Discoverer program was the recovery of a capsule ejected during orbit. Early unsuccessful attempts to recover the capsules were followed by repeated successful sea and mid-air retrievals. These have made many spot news headlines. But behind the scenes is the Satellite Test Center in Sunnyvale, California. It is an operating activity of the 65 94th Test Wing satellite. Here is the Air Force cadre, whose operational environment is space. The coordinated training effort is a result of Air Force management's determination for their personnel to keep pace with the rapidly growing operational demands in space. By means of direct line communication, the test center monitors all launches in the Discoverer program and controls all subsequent phases of flight and recovery. Orbital injection is verified by test wing tracking facilities. First reports come from the installation at Kodiak, Alaska. In sequence, the facility at Kaina Point, Hawaii, and the one in New Boston feed the data to the Satellite Test Center. After analysis, a change of instruction can be radioed to the timer in the orbiting Agena so that the capsule package will be ejected on the specific orbital pass desired. The Air Force developed Agena vehicle is being used as the upper stage for the Army's Advent program, for NASA's Ranger lunar exploration program, and for the Vela Hotel high-altitude nuclear detection system, of which the Air Force is executive manager on behalf of ARPA. Versatile and dependable Agena is also being used in the Midas missile detection and alarm system. Midas 1, launched from Cape Canaveral in February, did not orbit, but Midas 2, in an equatorial orbit, and Midas 3, launched into polar orbit from Point Arguello, California, successfully began laying the groundwork for the satellite system to spot missile launches anywhere in the world. Aboard Midas 3 is the 23-pound black box for HEPDEX, High Energy Proton Detection Experiment. It transmitted the first continuous information on the actual size and radiation intensity of the Van Allen belt. Preliminary quantitative analysis of data has revealed that the belt is only 1/2 as big in area of major radiation concentration as originally thought, and that it is 6 times as hot. The Satellite Inspector Program, formerly known as SAINT, is a first long stride toward our objective of inspection, rendezvous, and docking. Satellite inspectors, equipped with TV cameras, detection sensors, and relevant electronic equipment, will be launched on an intercept trajectory determined by ground tracking. Because military space systems must be operational around the clock, 365 days a year, the development of maintenance and repair techniques now under study must result in the capability of transporting Air Force crews as close in or as far out in space as may be required. Current concepts of system reliability have taken into consideration that future operations indicate the need for reusable systems, varied inventories, and space vehicles in large numbers. From the standpoint of economics, a continuous and expanding operations in space demand a decisive reduction in cost of boost. The current Blue Scout's solid propellant stages can be stacked in tailor-made combinations for boosting payloads from 25 to 1,000 pounds to altitudes of from 200 to 50,000 miles. Managed and operated by Air Force personnel, versatile and economical Blue Scout is supporting a number of inquiries, not only for the Air Force, but also for the other services and for industry to back up their research needs. For greater ranges and multi-ton payloads, solid segmented rocket motors 100 inches in diameter and capable of 1/2 million pounds of thrust are under development. In support of the overall program, management has diversified test facilities and qualified personnel at installations across the continent. Edwards Air Force Base in California's Mojave Desert has 16 static rocket engine test stands. A special stand is for use initially by NASA's 1.5 million pound thrust F-1 engine. The facility has the growth potential to static test rockets up to 6 million pounds thrust. The Special Weapons Center in Albuquerque, New Mexico conducts research, development, engineering, and testing in all fields of nuclear energy, including radiation effects and propulsion. SWIC space radiation instruments have also been carried and recovered as part of Discoverer payloads. South of Albuquerque, at Alamogordo, on the Missile Development Center's 35,000-foot sled test track, missile components and subsystems can be subjected to acceleration up to 40 Gs, to deceleration and vibration forces encountered during flight. Across the continent, in Tennessee, at the Arnold Center, many specialized high-altitude chambers test components for every major ballistic missile and space vehicle in a simulated space environment. The rocket test cells can handle full-size engines of up to 200,000 pounds thrust at simulated altitudes up to 300,000 feet. The various von Karman gas dynamics facilities can test models and components at velocities up to Mach 20. In support of the Mercury program, models of the capsule are tested under simulated re-entry conditions. Up the East Coast from Arnold Center, in Bedford, Massachusetts, the emphasis is on communication. Experience has already verified that electronic systems form our lifelines to space. Here, SpaceTrack was developed to gather data on satellites. Now, capable of monitoring about 50 objects in space at the same time, it is an interim air defense facility until NORAD achieves a complete operational capability at Colorado Springs. From worldwide sources of data, SpaceTrack records and plots the course of all in-space man-made objects. As of midsummer, 28 American satellites and 1 Soviet satellite were in orbit. Significantly, 12 American satellites were continuing to transmit valuable data. No Soviet satellites were transmitting. The Rome, New York facility has responsibility for development and test of ground-based electronics equipment and components for global communications, air defense, air navigation, and traffic control, as well as support of the intelligence community. An item of interest is the translating machine, which uses computer technology to translate Russian language documents. And a few hundred miles west, at Wright-Patterson in Dayton, Ohio, are headquarters for a vigorous concerted effort devoted to the research, evaluation, and analysis of foreign technologies, with particular emphasis on space capabilities. Also here at Wright-Patterson, the Air Force has the nation's outstanding facility for investigation of all types of phenomena related to manned space efforts. Air Force aeromedical programs date all the way back to 1918. Today, continuing research ranges from tests of physiological reaction under high forces of acceleration to final development of full pressure suits for aerospace vehicles and the complex psychological factors of weightlessness. Information on the effects of long-term weightlessness is one of the objectives of the Bioastronautics Orbital Space Program, which is designed for obtaining further information of deep space radiation and life support and environmental control systems. The bioastronautic effort is vital in achieving the system reliability we must achieve to ensure the protection of human life through departure and return. Our human resources are, as they have always been, our most important resources. It is true that the scientific disciplines must have facilities to create products of the mind, and that these in turn must be developed into practical hardware, which requires industrial facilities across a continent. These have been planned and funded and built in a cooperative effort with private industry. The scope and magnitude of these diversified resources can be seen and photographed. Human resources can also be seen, but you can't take pictures to show the knowledge, experience, or thought processes of 10,000 scientists and engineers in the Air Force family. And yet, that is their prime function, thinking and working and probing in many areas. For example, a fuel cell, which uses methyl alcohol and sodium hydroxide solution as fuel, and a hydrogen peroxide oxidizer. Plasma propulsion studies, linear pinch equipment to study magnetohydrodynamic turbulence. Ruby lasers for pinpointing such targets as satellites and for mapping planets in far greater detail than has ever been possible. There are many more, and after only 7 years of concentrated effort, the vehicles we build today are perhaps even smaller in relative size than the Santa Maria in which Columbus started his voyage to a new world. It is also true that physical size is not in itself a criterion of technological progress. But the rapid simultaneous advances of many technologies in many parts of the world have changed our traditional concept of time as an almost limitless resource to a very limited resource. But we do have expandable resources of experienced people to do the work and the requisite facilities where the work must be done. The requirements in space for the capabilities of reconnaissance, inspection, rendezvous, and docking are logical and necessary military requirements in the interest of national security. In the short 7-year period, the Air Force has achieved good progress in planning, funding, and building the physical resources. For the all-important human resources, the Air Force has worked to develop and train a cognizant team. We have the tools. The objectives in space must be clear and well-defined. They must be met within our limited resources of time. In the interest of national security over the full range of the aerospace environment, that ability to produce has been steadily advancing since 1954, when, for technological guidance and advice, the Air Force called upon its Scientific Advisory Board. And they responded, men like von Neumann, von Karman, Kistiakowsky, Millikan, Draper, Ramo, and Teller, Kaplan, Getting, Stever, and all the others. In the pioneering tradition of General Mitchell, they accepted the challenge. Development industry from the Pacific to the Atlantic. The purpose of this special report is to present a concise picture of the space resources which the Air Force has developed in order to acquire for the United States a new line of sight. The official Soviet announcement of their unilateral cancellation of the nuclear test ban was followed by the detonation of 14 devices within 3 weeks. The details of preparation for their special weapons tests must have extended over an appreciable period of time. Time itself has become a weapon, and the time element is an integral part of this report. It has been just a little more than 7 years since the Air Force initiated its accelerated ballistic missile program, which today is providing the nation's booster springboard into space. The success of the basic hardware of deterrence and space makes good copy. But the real importance lies in the buildup of the solid foundation of the total program, the coordinated human and physical resources that together mean ability to produce. Components, subsystems, whole systems, and the total weapon. Thousands of tests of subjection to conditions that show the real character of things and people. Neither things nor people are perfect. The planning, the effort, and the calculated risks may be important only to those who overcome the technological obstacles. or to the ones who make the management decisions, or the many others who follow through to ensure that R&D actually works. But what they have accomplished was called upon for diversified sources of production and people for new and exacting skills. They responded and they worked. Advanced new concepts have applied and proved out new disciplines of management, with all phases moving forward together at the same time. Development, production, site activation, support equipment, crew training. For easing the heavy weight of time, systems management is a powerful lever. The fulcrum is the critical examination and decisive trial of testing. Part